from the University of California at Davis. He is also an AIT alumnus from structural engineering, long time back. So I myself, I'm Penung Wanichai. I'm a professor of structural engineering. I will be serving as a seminar moderator today. So before we go on, I would like to invite our Vice President of Development, Mr. Serenda Shweta, to give an opening remark. Vice President.
Thank you. Thank you very much. On behalf of the President, let me welcome all the participants. And a special pleasure to welcome Professor Sashi, who is busy at the back. Special because we were together on campus, on the AIT campus. And as a student, Sashi demonstrated commitment and leadership skills as the SU president, and all of us who were together at that time, we witnessed that. So for the students who are in the audience, this is an example. I think if you're interested in an academic career, an example to follow. After leaving AIT, he had a very distinguished career, which we will hear from later about this career, including the chair of civil engineering at the University of California, Davis. He's somebody who has excelled from being a master's student to being chair, being adjunct faculty in other universities. We are at AIT especially honored that Professor Sashi could accept this distinguished adjunct faculty position, which is established by the President, as you all know. This provides an opportunity for alumni, for former faculty members to come back and be engaged with our institute to make sure AIT continues to be relevant. So I wish to, on all our behalf, thank Professor Sashi. Thank you for sharing your precious time. Thank you for your valuable experience and the knowledge that you have acquired. So thank you very much.
Okay, thank you, VP Shweta. Let me spend a few minutes to introduce the speaker, Professor Kunnath, to you. As I mentioned earlier, Professor Kunnath is an AIT alumnus. And currently he is serving as a professor at the Department of Civil and Environmental Engineering at the University of California at Davis. So he received his undergraduate degree from Bangalore University in India, and his master degree in structural engineering from AIT. That was, I think, around 1982. And then he continued with his PhD at the State University of New York at Buffalo. So that's his background, educational background. So during his career, he has published over 200 technical papers and reports. He chairs and co-chairs many international conferences and delivers invited keynote lectures in China, in Hong Kong, in India, Italy, Japan, Korea, Mexico, Portugal, Slovenia, and Thailand. He also formerly served as editor-in-chief of the ASC Journal of Structural Engineering. I think those in the area of structural engineering know how important it is of this journal. Okay, and he also chairs several ASCE technical administrative committees on Dynamic Effects and Technical Committee on Seismic Effects. Professor Kunnath has received numerous awards, including the 2012 Norman Medal from ACE, the Richard Torrent Awards in 2009, and many others. It's a long list, so I don't think I will go until the end. Okay? Well, still okay?
Almost.
Almost. All right. We still have time. Okay? So, actually, we have one announcement to make. Yeah, while we are waiting, let me give you an announcement. It's a request by AIT Solutions, used to be called AIT Consultant. It's an announcement with me. It's the first time for me to read it, so let me explain. There will be an event called Structural and Construction Engineering's Mobile Application Hackathon. Okay? And there's an award for that. The event will be on 23rd August.
No, it's okay. So which is it's here.
Which is
It's here, right?
probably tomorrow. Yeah, tomorrow.
That's right.
Yeah, in the afternoon. Okay, I think some of them will come and explain this later. Professor Kunnath, everything okay?
I think so.
Are you ready?
Yes.
Okay, I already introduced you to the audience, and if you are ready, please.
All right. Well, thank you, Professor Panang, for your introduction, and thank you, Surendra, as well, for those kind words. Coming back to AIT is a special moment for me. Like I said, I spent several years in the 1980s, so it's been a long time, and it's always wonderful to come back to this campus. AIT brings back many memories, both professional and personal. I met my wife, Lorna, here also. She was also doing her master's here from the Philippines in human settlements. And so we actually got married here in Thailand before we moved. And some years ago, I brought my children, Avinash and Amita, who finished their studies back in the US right now. They also had the chance to come here. And it was always a pleasure for me to show them where their parents met. And so, like I said, it's a pleasure. And now to have this honor of being the distinguished adjunct faculty, means a lot to me. And so I want to thank President Warsak, whom I hopefully will meet later today. So once again, good morning, ladies and gentlemen. For this talk, I decided to pick a topic that I have been working on for the past few years. My actual early research was in earthquake engineering, but the same concepts that we use there can be extended to other fields of study as well. So what I'm going to present today is a kind of a quick overview or summary of this field of what we call progressive collapse or disproportionate collapse, if you will. And I'm going to focus on reinforced concrete frame buildings. I mean, there are, the kind of modeling, techniques that we use for steel and concrete structures are quite different. So my focus here is primarily on reinforced concrete frame buildings, which actually constitutes a very large percentage of the kind of construction that you see, mostly, I would say, in Asian countries. A little bit of background and the objectives of the work I'm presenting. First of all, it is to get an understanding of the mechanics of failure in structural systems as a building system as opposed to a component. Okay, so why is it that buildings fail? If you lose a part of a building, what is it that what kind of load distribution paths they follow? And as a consequence, we can understand a little bit more about how we can design new buildings to avoid these kind of failures. The primary goal of most of the modeling work that I do is to come up with what I call, macro or simplified models. There are, nowadays with the advances in computation, there are fairly advanced tools where you can, use very high fidelity or refined continuum models. But these are extremely computationally intensive, and rarely can you use them to analyze an entire building system. Okay, so a lot of the focus here is on coming up with simpler models so that we can capture what happens under large displacements that these structures undergo in the proximity of collapse. And we have to, when you develop simple models, one of the tasks that we have is to validate them. We validate them in two ways. We validate them using complex or more detailed analysis, which, like I said, is time consuming, and we also validate them with available experimental data. Now, in this field, there's very limited, experimental work as well. So the limited work we have done, we were able to do some validation. And finally, we trying to understand what we call the robustness of a structural system. What that means is, given two building systems under the same kind of loading configuration, that if you were to lose, let's say, a column in the building or part of a building, how is one system, more robust than the other in terms of arresting this collapse and surviving a local failure? All right. So when we measure robustness, we are trying to understand how, strong is this building in terms of resisting these types of extreme loads. Okay, so ultimately that's the goal of this entire project in terms of progressive collapse and the development of simplified models. Okay, some of you might already know what is progressive collapse. Like I said, the other term that's used is disproportionate collapse, and as defined here by this is the General Services Administration in the United States. So progressive collapse is a situation where a local failure of a component leads to a larger or complete structural failure. If you go back in history, in 1968, this is the classic case of a localized collapse. If you look up here, this is a 22-story building in UK. There was a small gas explosion here. There was a lady in an apartment who was turning on her gas stove, and apparently there was a leak. And that explosion took out one of the small walls out, a bearing wall in that structure. These were the kind of buildings constructed in the UK in the 1960s. These were all precast structures. And the failure of one little wall here, as you can see, led to the failure of this entire section of this building. So this is a classic initial example of progressive collapse. So you have one local failure on the 18th story, and obviously when it that wall lost the capacity to carry the 4 floors above it, they collapsed onto each other, and finally you have a cascading failure. In the United States, many of you might recall this, the research interest in progressive collapse started after 9/11 when we saw the World Trade Centers come down. If those of you who recall, these buildings survived the heat and initial failure for almost an hour before they actually came down. So this again is a classic case of progressive collapse. But going back a little bit, so let me first of all define, so I use the word structural robustness, and so what we're talking about here again is the ability of a system to accommodate local damage, and prevent further failure of other structural elements. So actually, even before 9/11, in 1995, we have this building here in Oklahoma City, United States. It's a federal building constructed in the 1970s. It's a 9-story concrete and shear wall structure. Okay, so like I said, this happened quite a while ago, almost 20 years ago. And so what happened here was a car bomb was placed at the bottom here. This was an example of what we would call local terrorism in the United States. And the result of that car bomb was the entire building, as you can see here, came down. So what is progressive collapse or robustness in this context? If you look at, this is a sketch showing the blast crater. This is the crater as a result of that truck bomb that was placed here. And this is the final state of damage. As you can see, pretty much all the floor slabs and beams and columns in this section of the building came down. However, there were some fairly detailed studies done on this building when we examined the initial failure immediately after the blast. So it is our assessment that immediately after the blast, only a small section of the building was affected, only the first 3 or 4 floors. So this was the initial blast region. And if you think about the total floor area of the building is about 13,000 square meters. So the estimates from analysis conducted by NIST indicate that only 4% of the building was initially destroyed by the blast. Only 4%. But because, when these little elements here failed and the remaining elements were not able to sustain the loads above it, it finally resulted in 40% of the building being destroyed. All right, so again, this is a classic case of progressive collapse. So if this building were designed in a way that, once you lose some of these elements, if the loads above could be redistributed to the other vertical load-bearing elements, possibly we could have, saved part of the, much more of this building. So with that little background and introduction, let's talk about methodologies that we use to understand and evaluate progressive collapse. Okay, there are what we call direct analysis. Okay, in a direct analysis, you actually model the loading itself. Okay, so in other words, the load could be a result of an impact from some object. If you take a vehicle and drive it into a building, for example, that would be direct impact. Or if it were an explosion, you would actually model the shock wave. All right. But this is a fairly detailed and complex method of analysis, because not only do you have to model the shock wave, which is a wave propagation analysis, you also have to consider the removal of elements one by one. And every time you remove one element, you have to go back and reestablish equilibrium in your system. And then if equilibrium is not met, you go to the next step and so on. So it's a very time-consuming and detailed process. Okay, so that's what we mean by direct analysis. Okay, another approach is what we call indirect, or the terminology that's used sometimes is threat independent, which means we don't model the source of the loading, or we don't model the threat, but we consider the post-event situation, which means we assume that the load has already been activated, which means it could be a blast or it could be impact, and we assume that a structural element has already failed. Okay, and then we see what is the effects of the failure of that element on the building. Okay, so the word used again by GSA is the alternate path method. Okay, so the alternate path simply says that if you lose one element in a structure, what are the alternate paths available for this system to redistribute those loads? Okay, so in this case, we pre-assume some scenarios. Okay, so you've got to assume, okay, let's assume there was a blast or an explosion, a result of which we lose one column in the bottom of the building, or you lose two columns, all right, or you lose, beams and some columns. Then we go back and try to assess, what happens to the building, after these elements have been removed or lost. Okay, and we finally do the evaluation for the collapse of the building given that scenario. All right, so most of the work that we do or that we have done in this area has to do with what we call threat independent analysis. So much of what I'm going to show you here, from the modeling perspective, we don't model the loading, but we model the after effects of the loading. Again, I kind of mentioned this briefly that, when you do direct analysis, typically we also have the option to choose whether we want to model elements at fairly detailed levels or whether you want to, use a more approximate. Like I said, the goal of most of my work here is to come up with simplified models. So a microscopic modeling is when you use a continuum-based, what we call the finite element models. And here is an example of a 10-story structure. And here I've just taken out a small portion of that, which consists of 2 beams and 3 half columns. Okay, the way we do these simulations for component level is we assume that this column beneath this has been lost, and we try to do some simulations of this. So in the detailed model, as you can see, we break up the beams and columns into extremely fine elements, and we model not just the concrete, but we model the reinforcing steel, and so it becomes extremely complex in terms of the simulation itself. Now this is extremely good for analyzing local behavior, which means when you use models of this level of detail, you can go in and see what happens at every section in the concrete. You can go and examine what happens to every rebar inside that section. But like I said, it involves significant computational effort. It could take hours and hours just to analyze a simple section like this. So to analyze a full, a 10-story frame could take days, even on modern computers. So what we do, therefore, like I said, with macroscopic or simplified models, we use what we call component-based element modeling. So to show you an example here, for example, this little beam element can be replaced by a line element with just what we call fiber sections. So we just discretize sections of this, and then we can integrate along this to come up with the behavior of the element. Likewise, if you look at the joint, okay, the joint, which actually is very important in terms of the transmission of forces between the beam and column, okay, we can replace that whole joint region. Okay, this is a two-dimensional model by a set of rigid links and springs, and we can assign properties to these. Okay, as a result of combining this, a model of this nature reduces to something as simple as this, where you just simply have line elements representing beams and columns with fiber sections, and a joint element that represents the behavior within the joint. And the computational effort required to analyze something like this is orders of magnitude less than with detailed analysis. However, such models are obviously not adequate if you are interested in what happens at very local sections and extracting behavior at the local level. However, it's computationally very, very efficient. So the early work that we did was to come up with these refined joint models, because we felt that in looking at the system as a whole, we had to model very carefully the transition and the transfer of forces that take place. Remember, because the entire study of disproportionate or progressive collapse has to do with the load redistribution that takes place once you lose an element. And so we spent a lot of time in the early days looking at, this is work going back almost 10 years, where we tried to represent the actions within the joint and the transfer between the joint and the element itself. So you have, this is for a reinforced concrete element, where we model by using springs, the bottom reinforcing bars, the top bars, because eventually what actually causes failure here is the fracture of these bars at large displacements. Okay, we also model, the shear transfer that takes place between, because once a crack opens between the interface of a beam and a joint, we have to worry about the shear transfer that takes place between the elements. So, like I said, we have started off with different types. We've, then further improved it using fiber sections. But the key here is, how do you model the properties of these springs? So in this case, the rotational spring that represents the deformation of this joint, is represented by a moment rotation. So as you can see here, this is a fairly complex nonlinear spring. Likewise, if you then go to the shear spring here and the interface elements between the joint and the beam, we have, again, other types of spring models. So these are all nonlinear representations of these springs that you see here. So there's a little bit of work involved in calibrating the properties so that we represent the behavior of this joint. After this step, the early models, like you said, were all two-dimensional models, but later on we're looking more at three-dimensional behavior, and you'll see in a moment why. And this is the same two-dimensional joint. Now I'm looking at sets of parallelograms, if you will, in 3 dimensions, and so you can see how the joint deforms in 3 dimensions. And again, you can have the same type of shear springs in both directions. You have the moments, all 3 components of the moment, including a torsional spring, if you will. All right, so this is a 3-dimensional representation of the same beam column joint. The next aspect of modeling is what type of analysis that you do. I mean, those of you who are familiar with nonlinear analysis, for static and dynamic loads, you have both implicit and explicit methods. And so in this case, what you're trying to do is figure out, balance in terms of computational efficiency and convergence. If you use an implicit model, they're much more accurate, obviously, but it's extremely time consuming because it's always looking for convergence at the end of every step. On the other hand, if you use an explicit analysis, you're not worried as much about convergence at the end of every step, but you run each step at an extremely small time step that's controlled typically by the eigenvalue or the first frequency. So, if you have elements with very small mass, all right, your time step starts to shrink dramatically. However, most of the simulation that we've done both actually. Most of our modern simulations, we use explicit methods because it helps you carry through the process to the end of the analysis. Whereas with an implicit method, quite often when you don't reach equilibrium, the analysis fails and you don't get eventual results. The other aspect of modeling is whether you do 2-dimensional or 3-dimensional models. And in this case, as you will see later on, we have found that the effects of the slab and the membrane action of the slab is extremely critical to the overall response of the system. And so most of the analysis, like I said, that we do now is all 3-dimensional. Okay, let me highlight that here with 3 models that you see here. Here is a 2-dimensional assembly of a simple section of a frame. Okay, this is just using 2-dimensional models. This is the same model, but now I have the three-dimensional aspects built in, so I have all the frames in both directions. This is just a simple 2-bay by 2-bay single-story analysis. And finally, I add the slab. So here the slab is not included, just to show you the difference if you do a two-dimensional model versus a three-dimensional model where we don't include the slab, and finally a three-dimensional model in which we do include the slab. And here are the results, as you can see. So what we've noticed is that very large deformations, that the model in which we include the slab shows the ability of the system to survive much higher loads. Okay, so if you use a two-dimensional model, you will completely underpredict the ability of the system to resist forces. So this is actually a good thing. So you can call this highly conservative, but your estimates in terms of the load carrying capacity will be a lot less. Okay, so that's why we feel it's very important to look at three-dimensional models where we also consider the effects of the slab. Then coming down to the material level, remember, so now I'm talking mostly about the component, the fact that you have to model the beams, the columns using fiber section, the joints, and then what about the materials? Now, if we talk about reinforced concrete structures, we have steel and concrete. In terms of reinforcing steel, okay, what we found is that, especially, remember, we are now modeling systems at extremely large deformations, and failure happens when you exceed the peak value. And so what it turns out is it's mesh sensitive, okay, which means depending on how you discretize your reinforcing bar, your path, load path after it hits the peak, the softening response is different. Okay, so it's extremely important to model, to pick the correct length size so that the stress strain behavior that you represent of the element is correct. This is on the tension side. It's also true on the compression side. On the compression side, the bar tends to buckle. All right, so here, as you can see, you get a nice path in which you have you'll have a plateau followed by strain hardening and softening. But on the compression side, when you apply large compressive loads and reinforcing steel, it tends to buckle. And so we've spent a lot of time coming up with models to include the effects of buckling in reinforcing bars, which, like I said, in modeling progressive collapse, these are extremely important aspects. And occasionally I put some notes here about papers that have been published on these topics. That's steel. Likewise, with the concrete, modeling the concrete is also important. These are classical studies done by Van Meer going back to the 1980s, where he tested cylinders of different sizes and showed that the stress strain behavior is affected by the size of the cylinder. Okay, so what this means is also when you do finite element modeling, or even in our case, when we model elements at different scales, you have to be careful as to the size that you assign, because the resulting stress strain behavior is going to be different. So we have done, like I said, so we do some calibration studies so that the expected behavior is the same as the material behavior at the length scale in which you tested your component. All right, so this is kind of important. So if you start to go to smaller scales, then you have to be aware of the fact that, in fact, you'll end up with a different stress strain curve depending on the size of the element. So these are little details that you've got to keep in mind. The final thing about material modeling that I'll talk about is bond and bond slip. Okay, for those of us who work in reinforced concrete, we recognize that once you get into slightly large deformations, there is a slip that happens between the reinforcing steel and the concrete. So the question is, how do you account for this in a simplified model? Okay, so the way and some of the reasons we do that is, you could get premature bar fracture as a result. If you assume that it's fully bonded, okay, you're going to get, the bar fracturing much earlier than it actually should. Okay, and also you have to consider so-called anchorage failure modes. Remember, because you have your bars that are anchored in the joints or at the corners, and if you don't consider bond effects properly, you're going to get premature anchorage failure as well. So what we have done is to essentially modify the stress strain behavior, and the way we do that is if you look at the critical zone in which we expect the bar to slip. Okay, remember, this is where the crack is going to open, right? You have an opening of a crack here, so we consider this little zone here, and we account for the slip, S as a function of that little length. Okay, so we can then essentially modify our effective strain, which also accounts for this bond slip. So this is kind of an indirect way to modify your stress strain behavior of your steel in the zone where you expect slip, and this somehow indirectly accounts for bond slip as well. And we've, of course, validated some of these models. So finally, putting it all together in a system, here's your slab, your beam, and your column. And as you can see, we're simply using line elements. But each line element we use beam elements with what we call cross-section integration. What does that mean? Which means that each cross-section here, we have fibers in each direction where we can model the reinforcing steel and top and bottom. And then we can model the concrete core, which has different properties than the cover on the outside. And likewise, you can model the properties of each reinforcing steel. Okay, this is how we model currently our slab. We're using a layered shell. Okay, a layered shell is a lot more efficient than using a three-dimensional finite element model. But the key then becomes how do you tie the nodes of the beam and the slab. Okay, as you can see, they're not occurring at the same, because remember the beam cross section, the behavior is reflected at the centroid of the section, whereas the slab is offset. So we have to kind of account for the reference axis of both. And then finally, the interface. Remember, we talked about the interface between the joint and the beams and the columns. Okay, so we also have to take into account the interface behavior where the shear transfer takes place and also the bond slip behavior takes place. Okay, these are some details about how we constrain the nodes so that we get accurate representation of how the beams and slabs work together. And again, the joint, like I said, we've modeled our joints sometimes assuming that they are rigid or by assuming a flexible joint. And this really depends on the type of connection that you have. So if you're looking at a what we call a non-ductile connection, the type of connection that you'll find in non-seismic zones, then we find the need to represent the joint deformation. But if you're looking at a very well-detailed concrete joint, then we can make the assumption that if it's rigid, it'll save you a lot more computational time and the results are acceptable. Okay, so that was kind of a quick overview of the different types of models, both at the element level and at the material level that we've tested, and now we try to validate how these models are performing. Okay, so the validation includes, like I said, comparison with detailed models. So this is a detailed finite element model in which we have every column. This is just, as you can see, this is a 2-bay by 2-bay section of a building where we applied gravity loads. And we've modeled the slabs as three-dimensional slabs, and likewise, the concrete and reinforcing steel is modeled to great detail. Okay. On the other hand, this is our simplified model where our beams and columns are represented by line elements using fiber sections, like I explained, and our shell is simply a layered shell element. So it's much more, computationally efficient than using a detailed model that you see here. And in this model, as you can see here, we can capture what happens in fairly great detail to every reinforcing bar. So in this case, at large deformations, you can see actually the fracture and separation of the bars. Okay. On the other hand, that kind of information obviously cannot be obtained in this model, but we overall get the overall information. And so here I show you the comparison between the detailed model that you see here and what I call the reduced order model that you see here. Again, and the results are acceptable in both cases. And what's the difference from the computational perspective? As you can see here, the detailed model, we had over 220,000 elements in this little small section that you see here. So you can try to translate this if you want to analyze the complete building. And we ran this on 8 processors running simultaneously on a parallel system and took about 17 hours. On the other hand, the reduced model that you see here, is, as you can see, just 2,000 elements, and the total solution time to get the same results is about 34 minutes. And so this is what I mean by saying, we focus on these reduced order modeling, but we spend a lot of time validating and making sure that the results that we get from these models are acceptable. There have also been tests, and these are full-scale tests that have been conducted, fairly recently in the U.S. As you can see the side, these are, where we push down on one of these, beam column connections. These are 2 beams, and this is where we simulate a lost column, and we push down on this to very large displacements, and then we try to validate. Okay, in this case, I'm showing you some results from detailed models where we can, capture the crack patterns observed in the test and what we simulate. But on this side, I'm showing you the results of the experiment and the detail and the reduced model. So here you're looking at both a very fine, finite element model versus the reduced order model that I just described earlier. And you can see it captured, this is the applied load here, there's a load applied in the center, and the displacement, the vertical displacement. And you can see the displacement shown in inches. Okay, so I don't know if you can convert those inches, but you're talking about 30 to 40 inches, which is like pretty large in terms of the overall displacement. And here I have another plot showing the horizontal versus the vertical displacement. Remember, when you push down on this, you also get a horizontal movement inward, all right? And as you can see here, that our reduced order models are able to capture the experimental results fairly well. Okay, so again, so this gives you confidence in the modeling abilities of the techniques that I've just explained here. Okay, so what did we gather? What did we learn from this in terms of the behavior of a reinforced concrete subassembly? So here again, we have these, this is 2 bays, and here's your central column where we assume this part is removed. And when you push down on this, there are 3 phases of behavior that you see here. The first early portion is when you have essentially a flexural response. And then between that and this stage, this is essentially all, and the load transfer takes place by what we call arch action. Again, those of you familiar with reinforced concrete, this is pretty much what we study in terms of standard design. But if you want to design for collapse where you then exceed, these limit states and you go into what we call the catenary state where the beam is pretty much carrying the entire load in pure tension. You see, you have a transition from compression to a state of pure tension. And so in that case, the concrete doesn't do anything. All of the load is carried just by the reinforcing steel inside these segments. And so the failure eventually is also controlled by the fracture of the bars. And that's why, when we talked about material modeling, it's important that we consider the softening phase as well, the post-peak behavior of the reinforcing steel. These are another test. This is a 3-story building. A single frame, a 2-dimensional test that we did some years ago. This was conducted in China. And again, like you can see here, I've shown some load displacement path comparing the test to simulations. And as you can see, we've done an extremely good job, especially in a 2-dimensional sense, of being able to reproduce the observed behavior in the laboratory. At the end of it, so some years ago, one of the interests in the United States was to figure out, okay, how do we detail your connections to resist progressive collapse? And so there was some interest about comparing seismic versus non-seismic details. So what we did was we took this 10-story frame and we designed the components in 2 regions in the United States. One, what we call the seismic design category SDCC in Atlanta, which is a non-seismic zone, and another seismic zone in Seattle on the west coast where, you have, the probability of seismic events are much larger. And just like in any other part of the world, a seismically detailed connection has much more reinforcement, the sizes will be different and so on. And I very quickly show you here some details, the difference between a non-seismic connection and a seismic connection. You'll very quickly see that the joint reinforcement, there's a lot more joint reinforcement, there's more reinforcement in the potential zones where we expect plastic hinging, whereas in a non-seismic zone, the amount of reinforcement, as you can see, is a lot less, all right? So we did a very quick study to compare the performance of these 2 structures, and what we did is, again, the same 2 frames that you see here, and what we did was to remove 2 columns. We removed 2 columns from the bottom story, and we simulated this using our computer program. And again, for those who are interested in modeling, depending on some software, you can simply specify a load removal. Whereas if you have a software that doesn't do it automatically, the way you do it is if you remove a column, you figure out the axial load that was supported by that column. So you place it initially as a load acting upward, and then in a very short duration of time, you apply a downward load. So essentially, you are simulating the sudden removal of a column, all right? And here I show you the comparison between a non-seismic and a seismic detail. Okay, and as you can see here, essentially you get a progressive collapse in the case of a non-seismically detailed element. Here I'm showing you the axial force in a couple of the column, some of the columns here close by at C1, B1, D1, and so on, where you see the transitions. Likewise, I'm showing you here the axial forces in the beams, because what we're trying to see here is, when you remove these elements, how are the loads that are carried here transmitted to the other elements, okay, and whether they are still able to resist those forces. And looking at these, time histories of the column axial forces and the beam axial forces in those critical zones give you some information. And ultimately here I'm showing you the displacement. So this is a non-seismic, element here. And so when we monitor the displacement at this point, as you can see, as soon as you remove those 2 columns, your displacements, exceed. This is actually in millimeters. So you're talking about 6 meters of displacement. Of course, so essentially what it tells you here is, because this program is not capable of, identifying failure, but it simply tells you, yes, in this case, you essentially have failure because it does not return back to stability. Whereas in the case of a seismically detailed element, we were able to show that around 50 millimeters, you got a peak displacement of 50 millimeters in this case, and then it kind of stabilized and did not fail. Okay, so so this was an early studies that we did with two-dimensional systems to compare different types of structures. Okay, so now I want to move on to a little bit about actual tests that we've done, and this is a fairly significant experiment that we did some years ago, again, in China. Like I said, I have some collaborative research going down there, and I want to acknowledge my colleague, Professor Yan Shao. And so what we did here is we built a large-scale 3-story model. And these are some of the dimensions. This is a 3-bay by 3-bay story, a 3-bay by 3-bay structure, reinforced concrete frame, actually designed to US non-seismic detailing standards. I have some pictures here showing you, the construction. That's the first floor, and also we, doing something like this in the US is not as easy. So in China, we were able to access a piece of land right outside the university, and we built the structure just to enable to do some of our collapse testing. So talking about the collapse, the question is, how are we going to remove these columns? Okay, so we designed the columns to be removed in a very special way. As you can see here, this is the column, and we placed some concrete blocks, and we held them together, and we held the top and bottom of the column together with some steel frames. And just before the test, we removed these steel frames, and we use a kind of a gas gun to kind of impact these blocks to take them out one by one. All right, so before we did that, we have to make sure we were successful in doing it. So we built, so this is an example of that. This is kind of just a vacuum gun which you can shoot a projectile. And so what you see here inside the laboratories, we have the same set of blocks, and here's the gun that you see here. So we're going to shoot a little projectile at a pretty high velocity to make sure that we can actually damage this. Okay, now why do you think that's important? Because this block is actually, as you can see, there's a little actuator here that's actually applying an axial force that represents the weight of the 3 stories above it. So there's a very large axial load. So if the force of this projectile is not large enough, you probably won't damage this column. Okay, so we did some initial tests, and if this little thing works here, I can show you a quick test here. So if you observe, this happens very quickly. And so as you can see, we were able to first demonstrate that actually, yes, that, with that, as you can see, there's an actuator up there that was supporting this load, and we were able to show that, we had confidence that we could take these columns out. And so the test here consists of the building. As you can see, we did 3 tests. In the first test, we removed 2 columns, this one, and followed by this column here. In the next test, we removed these 2 columns in the long span. You can see this is a shorter span. These are about 3 meters on this side, and these are about almost 4.6 meters. So we removed 2 columns here, and the shaded section that you see here is the loads that we placed. Okay, and finally we did a final test where we removed a central column. Okay, so we were interested in several things. What happens when you remove columns in the corner of the building? When you remove, again on the exterior side, when we remove 2 columns. So remember, so this beam span now is almost 13 meters. Okay, carrying a pretty large load, 3 floors above it. And like I said, so that was the last test here that we conducted. So here I only have a few things to show. I don't have all of the tests. But before we did the test, we also did some pre-test simulations to make sure that we were getting the results that we expected. I'm not sure if this one works. Okay, this one still works. So we remove a corner column, we remove a side column, and then we remove a central column. And we had to do these simulations to figure out whether we could do 3 tests without actually damaging the whole structure. All right, so we had to figure out how much load. So these are all what we call push-down analysis. So we take out a column down here, then we push down on this to see what loads it would take to collapse this building. So here actually, I think you don't see this here, but if I can. All right, so the purpose of doing this kind of simulation is to figure out what level of forces that we needed to apply on the building to actually collapse the building. Okay, because we didn't want to do a test and not apply sufficient loads and actually have collapse. Okay, so that's just to simply illustrate that we did these numerical simulations, what we call pretest simulations, followed by comparisons of the loads that we needed to reach this collapse state. Let me go back here. Okay, so here is a video of this simulation removing one of the columns. So I'm just focusing there on just that one corner column. Remember, this is the second column that we removed. Okay, so we observe very quickly again. So that's the same simulation that you saw in the lab, but now that's the actual building where we removed the second column. Okay, now if you look at, you think that removing two columns in a building is probably going to damage this, but as you can see here, the displacements under node A1, which is this node here, and node B1, after we remove two columns, the maximum displacement we observe are only 20 millimeters. So essentially, this building, is fairly robust in terms of, even after removing two columns at the bottom of the building, it's able to survive and carry its gravity loads. Okay, in the next test, I'm not going to show you this one, but here, which is probably the most critical test, we removed these two columns here. And so here's again another video showing you that the three-story frame, and you can see here we have applied we've applied, I think, about 2 times the actual design loads here, maybe 2.5 times the design loads, because this is what we figured would trigger a progressive collapse of this local region. All right, and so once again, I have a short video capturing this again. So I wanted to keep in mind several things because some of them happen fairly quickly. So after we removed the two columns, initially we didn't observe much. We saw a sudden, a short drop, and then we had to wait for some time before we actually observed failure. Okay, so we've actually now removed two columns. Okay, I didn't show you the removal of this one. We just removed this, and we had to wait 15 minutes before we actually saw a sudden drop. I don't know if you caught that. Okay, so we do have columns placed under that because we didn't want the whole building to collapse. We had to preserve it. So eventually we had a localized failure in this region. But like I said, we had placed some steel columns here because we still wanted to keep the building. But if you look at the displacements and if you look at the crack patterns at the top and bottom of the floors, you see a classical, in concrete, what we call E lines that that we were able to observe. And again, at every joint, we essentially had fracture of the rebars and fairly extensive damage at the corners where we had these large rotations. And if you look at the displacement, as a function of time, so the initial displacements are fairly small. It was less than 100 millimeters, all right? And then all of a sudden, as you notice, it suddenly jumped, and then we had what we call, from a frame mechanism, we were able to move to a catenary mechanism, and we have displacements of the order of about 350 to 400 millimeters. Okay, so what the transition region between frame and catenary mechanism is typically the depth of your beam. So once the displacement exceeds the depth of your beam, essentially you have pretty much tension in your reinforcement in your steel, and essentially those beams are resisting your loads primarily by tension as opposed to arch action. All right, so that kind of is an overview of some of the work we did in modeling and simulation. And like I said, the goal eventually of doing these simulations of buildings and so on is to come up with measures of robustness to see how do you compare two buildings, okay? How do you say that one building is more robust than the other? And the kind of approaches that we've used are essentially what we call deterministic approaches, where we specify which element is to be removed. Okay, so you can either remove columns one by one and conduct what we call the so-called push-down analysis. So you remove a column and you push it down to see how much load it can take, or you remove multiple columns and you keep pushing them down. And then to assess that, essentially to see whether these structures can resist gravity loads. So the question that came up during our studies is, okay, what should be the order in which we remove these columns? Do we randomly remove them, or do we remove them in a particular sequence? So we actually did a fairly detailed study that has been published since, where we determined that the column carrying the largest fraction of the applied gravity loads is the next critical column in a structure. So we've done some studies of this nature, and we came up with an energy-based index where what we figured out is when you remove a column, there are two things that are happening. On the one hand, you're going to get large displacements, and then you're going to see a sudden increase in the kinetic energy. Remember, this is a dynamic removal of an element, so you're going to get a kinetic energy, and then if you monitor both the kinetic energy and the strain energy, you can then see whether there's a balance. Okay, so either you reach an equilibrium state where the strain energy is able to balance the kinetic energy, or if the thing continues to drop, then of course your kinetic energy is going to exceed that of the strain energy. All right, so we use these energy-based index, and we came up with a kind of a measure where you're looking primarily at the kinetic energy of what we call a local region and a global region. I'm going to show you what that I mean in a second. And we define a damage index with a multiplier here, which is the deformation, the maximum deformation that takes place at any node. I mean, like I said, this is kind of a quick synopsis of what we did. There's a lot of studies that went into coming up with an index like this. And so what I mean by the local area is essentially if you were to remove column B1 here, then the local area are the beams and columns and the slabs connected to that. So the local area here is just this one shaded here. Likewise, if you remove two columns, let's say B1 and B2, then your local area shifts to this region. So going back to that index, okay, this index, the local versus global, we are referring to this local area versus the global area of the entire system. So we monitor both the kinetic energy and the strain energy in all of the elements associated with the so-called local and global areas. All right, and so we essentially apply the gravity load, we remove a column, we check the damage index, and then we determine this threshold limit. And typically, I mean, this again is part of a validation study where we found when that damage exceeds about 0.5 to 0.6, you're essentially on the verge of collapse. All right, if not, you remove another column and keep repeating this process. All right, so we did some case studies on a 5 bay by 5 bay building. We looked at two buildings, a 3-story, a 6-story. We've also done a 10-story building. And there are many factors that go into why we are looking at buildings of different heights, because the taller the building, the more floors it's supporting. Okay, so it's the failure paths that we observe here are quite different as you go to taller structures. Okay, here I think we've lost our video, so I have some videos to show for which I need to exit this and get to my... Okay, so here's a 3-story simulation. And so this is monitoring the displacements. So you see I removed one column, I removed a second column. So we had to remove 4 columns to get, so these are the maximum displacement that you're seeing there, and they were about, as you can see, 10 to the 3, which is about almost 2 meters of displacement. So that's the middle column removal. So we've done simulations comparing the, this is the same thing. The previous case I didn't show the slab, but now since I'm removing a corner column, you can see it a little bit more clearly. So I put the slabs back on here. So we remove 1, 2, and then finally a 3rd column here. And so what we were able to demonstrate here is that when you remove a corner column, it only takes 3 critical elements to cause failure of the structure. Whereas when you started off with the middle column, it took 4. Okay, and if you remember the previous slide. So essentially we're trying to see what is the critical path and what are the things we need to focus on. So clearly in the case of the 3-story building, it turns out that a corner column is much more critical. The loss of a corner column is much more critical because if you lose neighboring columns next to it, the building is most likely going to fail much sooner. Then we went to 6-story buildings to see what is the effect of story height. And so I'm going to start here again with the middle column. So going back to the 3-story, we removed 4 columns, but we actually did not observe failure. Okay, we reached fairly large displacements, but the system actually did not fail. When we went to a 6-story, on the other hand, because now this 6-story building is supporting a lot more load above it, now when we started to remove these columns, we actually did get progressive collapse. So the way we do the simulations is we first apply the gravity load, we wait, we remove one column, we wait for it to stabilize, then we remove the next column, we wait for that to stabilize, and then we remove the next column and so on. So in this case, we only had to remove 3 columns to observe failure. Okay, just so to recap, so in the 3-story case, we had to remove 4 columns in the middle to get a failure, whereas when we went to a 6-story building, we found that again, in this case, because it was supporting much more axial forces above it, we only needed 3 columns before this, we had a localized failure in this zone down here, which you'll see here. And again, looking at the displacements, you can see it's again of the order of about 3 meters or so. Okay, I have one more simulation to show, and that's the 6-story on a corner column. Oops. Let's start this over again. Okay, so again, we apply the gravity load. We remove the first column. Again, as you can see, the displacements are very small, about 10 millimeters. We remove a second column. Now the displacement have increased. Now you remove the third column, and then you're going to get a failure of the system. So these are the kind of studies that we're doing numerically to get a sense of, what are the critical sequence of columns that lead to failure of structures, and understanding this kind of behavior will then help us to design structures to resist, localized failure. Of course, at some point, you remove enough elements, you're going to get failure of the system. Going back here to the, so I'm going to, and so here again I have some numbers here talking about that damage index, where you see here once it exceeds the third column removal for the 3-story, we're going to get failure of the structure. Okay, I'm skipping through these because those are the videos that I just showed you. And I'm going to conclude now with a couple of slides, first talking about some of the limitations of what we've done already and what are some of the ongoing work. And in this case, like you've seen, we've only looked at failure of the columns on the ground floor of the building. I mean, typically we understand these to be the most critical because they carry the largest level of axial forces. However, we have seen in cases where you also remove elements on the intermediate floor or a top floor of the building can also lead to failure. So that's some studies that we're doing right now. Like I said, failure of upper level elements, which could either be beams or columns or a combination of both. We also, when you're looking at failure of upper story elements, you also have to consider the impact of those things falling on the floors below it. Whereas if we're on the ground floor, we don't worry about that much, all right? We also have not spent enough time looking at more what we call non-ductile details. You're looking at modern buildings versus older buildings where you have other failure modes like shear failure in short columns, splice failure. I mean, this is another critical thing because remember, when you have a building, the critical regions in a beam may not be at the joints, but it will be in locations where we have splices. And finally, we've also done some initial studies on shear wall structures, and this is some of the work that's still ongoing. So I have some conclusions or takeaway from this short presentation here today. First is that when you're looking at what we call reduced order modeling, there are 2 things we need to do. One is to validate these models both at the material level and at the component level, especially when you're looking at large deformations. And what we have found from our studies of reinforced concrete frames is that the load transfer that takes place is a kind of a 3-phase phenomenon. Okay, you start off with arch action, which is what we are familiar with in traditional concrete design. For those of us who do earthquake engineering, we're also familiar with plastic hinging, which is when the first section yields. But when it comes to progressive collapse, we eventually also have to model what we call a catenary response or large deformation response, in which the elements are resisting forces primarily by tension. All right? Okay, what we've also seen is that we do need to model our structures as 3-dimensional structures, and we have to include the effects of the slab, the floor slab, because the floor slabs do contribute significantly in resisting loads. Okay, and so the membrane action of these slabs do help structures survive, disproportionate failure. And the so-called alternate path method, which I said, which is an indirect analysis where we don't model the loading itself. As you can see in all our simulations, we don't model the load, we simply remove the column, assuming that removal happens because of some loading event. And that we think is an effective way of understanding progressive or disproportionate collapse. The problem though is we can understand the load distribution and so on after you remove the column, but what it does not tell you is the so-called reserve capacity of the system after you remove it, which is why in what we have done in terms of understanding robustness, we have spent some time looking at these energy-based indices to figure out the proximity of the structure to collapse, or how close is the system to failure. And in this way, we are able to compare the performance of two different types of buildings. All right, and so with that, I think like I said, we are also doing we're doing more research on robustness, and hopefully in the next coming years we will have additional work. There's a lot of work actually going on all around the world on this whole topic of disproportionate collapse. Right. So with that, I'm going to conclude my talk, and we'll hopefully have time for questions. Thank you very much.
Thank you very much, Professor Kunnath. Very interesting talk, and I think you all agree with me that this looks like a very interesting research subject, and many more can be done along this line. Now is the time for questions and answer. I'm sure Professor Kunnath will be willing to answer any questions from the floor about this topic. Of course. Any questions now?
Graduate students are always, we have somebody with a question.
We don't have, okay. Samita, please keep the microphone.
Thank you, sir. My question is that all the studies that you have shown in this presentation of the progressive collapse has been done for gravity load. I want to ask, has any study been done for such progressive collapse for lateral load as well or not?
Yeah, that's a good question. And like I said, my initial research was in earthquake engineering, so we were more interested in lateral loads than gravity loads. Yes, there have been studies done. We've done some work on progressive collapse under earthquake loading some years ago. I mean, I obviously didn't present that today. The focus today was mostly on the loss of elements and whether it can resist the remember, even in the earthquake situation, when the earthquake happens and you lose some elements, and if the earthquake, remember the earthquake load is gone, the goal eventually is to see if this building can still stand to support its gravity load. So a lot of the focus has been on the ability of structures to sustain the loads for which they're designed after the event. So the event could either be an impact load, like I said, or a blast, or as in the case of lateral loads, like you're mentioning, it could be an earthquake load. All right. So there have been studies. Some of them actually have been published about just looking at the response of structures under earthquake loading, in which case you do see progressive collapse as well.
Okay, thank you,
so there have been studies, but today I was not able to present any of that work. You can use similar models that I have presented to also study the situation of earthquake loading.
Okay, thank you so much.
Are there any other questions?
Yes, a good question. Yeah, so this is also, like I said, the goal of our studies eventually is to come up with new design methodologies to prevent so-called, disproportionate collapse. So there is actually a big effort in the United States under the ASCE, American Society of Civil Engineers. I'm part of one of the groups there. There are different groups looking at different structures. Okay, there are people looking at steel structures, concrete structures, and so on, and figuring out. Okay, so the benefit of this kind of numerical studies we're doing here is to understand these load paths. Okay, we realize that when you remove a critical element, the load has to be redistributed elsewhere. So how do you provide detailing requirements for reinforced concrete or connection details for steel structures to prevent the failure of neighboring elements? Okay, so yes, there's a lot of work going on improved details to prevent such what we call disproportionate collapse. Up to a limit. So we cannot design a structure to remove like 6 columns and still survive, but you can design a structure to lose 1, maybe 2, And so these are called continuity requirements. For example, they will specify where you can splice your bars and what kind of requirements you need for the splice to make sure that you don't fail the element. You can also put limitations on anchorage requirements and so on, the amount of steel that you need to pass through the joint. So these kind of details are being worked out, and so hopefully some of the studies that we are doing will help in improving these design details.
Okay, and any other question? How about from AT Solution Group? No?
I think graduate students and others are typically shy to ask questions. I mean, this could be interesting research topics for your master's thesis, so you can start thinking about it.
Could be. May I just ask a few?
Please, yeah.
I think you focus on kind of the effect of progressive collapse initiated by the loss of column. I think it's connected to the blast loading, right? But if there is a real blast loading, it may give an impact also to the slab, to the beam as well. But that seems not to be included directly in your analysis.
That is correct. Yeah, we are not currently. Yeah, currently our initial studies have been just on column failure. But just to mention, right now I have a student who's currently finishing a PhD, who's looking at failure of upper, story elements, and looking at the combination of the loss of, let's say, a slab, the supporting beams in a column. So we're looking at like the failure of 3 elements simultaneously. But again, these are all after the event. So we're going to assume the event has taken place and you lose some elements. Okay, today's presentation was mostly on the loss of columns, but the current work that we're doing is extending it to the loss of multiple elements at the same time. So, I mean, again, it's quite easy to do here. All we have to do is remove that slab or remove that beam. The actual failure process, is much more complex. You may only lose a portion of the slab and a portion of the beam, but the assumption that we make is that we've essentially lost the load carrying capacity of that element, the complete load carrying capacity of that element, and what that does in terms of redistributing the loads.
I kind of understand that. I think the most important element is your numerical model.
Yes.
Because once we have a reliable numerical model, then we can go on, study many possible cases.
Exactly.
But what I cannot understand is why we have to create a new index like energy-based index. Because if you have a good enough numerical model, maybe that is more direct, allow us to see the different pattern.
Okay, so the reason for that is, not all engineering firms have the ability to do detailed nonlinear analysis. Even these are simplified models and so on. It still takes some skill to conduct these analyses. And so the purpose of doing these so-called simplified damage indices, so though I've shown you these simulations for under dynamic loading conditions, you can also do them under static loading conditions. So somebody could use a simple program, a linear analysis program like SAP 2000, which they use in design offices. They could take out a column and they could actually measure the displacements and forces and compute some simple energy indices. All right, so the idea here is to provide some tool for the engineers to just remove a few elements and to see what they observe in terms of the sudden the increase in displacements, even if they are linear. Because what you observe in the nonlinear sense is that the displacements amplify, and all of a sudden you get a progressive failure. So even in a linear context, you're able to get some idea about what your critical elements are and whether you might or might not have disproportionate collapse. So the goal of that work, I agree with you, is that, if you just do the complete simulation, you don't need indices. But if you don't have them, we still have to resort to some simple way in which engineers can use an index to say that this building is more robust than the other building. All right. So in other words, if you have 2 buildings which you've designed differently and you remove an element, you can apply some index after you remove an element to see if like I said, we've looked at ratios of strain energy to kinetic energy and other measures as well. It gives you some idea as to which structure is able to, resist the load and the loss of elements much better.
In that case, the index must have a very good correlation with the simulation result. Otherwise, it's can be misleading in some case.
It can be, you're right, and that's why my last bullet point was we need additional measures, and so what I presented here today was an initial study based on some of the cases I've shown you, and so based on that we've come up with these indices. But I agree that if you want to have a general index, because right now, in fact, I'm talking about my current student who's finishing her work. We've looked at a range of indices from energy-based to simply displacement-based, and so we're coming up with a kind of a summary, which shows that, in fact, what we find is that depending on which column you remove, if you start off with the corner, or if you start off on the side, if you start in the middle, then different measures of damage will give you, better results. So one index may not capture the failure for, all kinds of possible failure modes. So in that, from that point of view, I think there is still open research on some of these topics.
Okay, thank you very much. Okay, I have asked many questions already. How about the floor? Any more questions? For what? Can you use mine? It's okay. That is all.
My question is about that you showed a comparison of two frames. One is properly detailed for seismic actions and the other one is not properly detailed. Can we generalize, as your data also suggests, that non-seismically designed buildings are somewhat at more risk for this progressive collapse effects? And will your recommendations for both kind of structures will also be different to make them more resilient against this type of failure?
Yes, again, good question. So, like I said, so that study was kind of focused study that, in the early days, there was a lot of interest where people said that a seismically detailed building, you're right. So, in addition to the work that I have presented, there are others who have looked at the same topic and they've come to the similar conclusion, which might be obvious, when you have a better detailed connection, of course, it's going to resist more load. But your follow-on question about, I do think that the kind of recommendations we make for non-seismic versus seismic is going to be different, because in a seismic region you are already going to detail your structures for seismic loads, and they are going to perform better. But even in that case, we have shown that you can still get failure. So if you want to prevent that kind of failure, you can take measures, additional measures to prevent that. So if you take the case of a building in a non-seismic zone, like I said, maybe just 2 columns might cause failure of the building. In a seismic zone, it might take 3. So the question then is, okay, what will it take to remove 4 columns in a seismic zone so you can, improve some of the requirements? And I agree that the requirements on both regions will be different.
Okay, we already have about 3-4 questions, and you give a very clear answer to all this. So I think it's time to close the seminar. This the 6th AIT Distinguished Adjunct Faculty Seminar today. Thank you very much, Professor Kunnath. Let's join me to show our. Before we leave, there's a group from AIT Consultant Solution want to make announcement. Please come. It's a short announcement that I could not do it properly. So, can you explain?
So, can I plug my USB here so that everybody
Okay. 2 minutes, huh?
Yes.